Welcome again, it's Mr. Boothman. We are jumping into section 4.3, which is geometric sequences. So last section was about arithmetic sequences, and now we're talking about a different kind of sequence called geometric sequences. So let's look at what the definition of this kind of a sequence is. So this is the form that geometric sequences take. And let's think about it. Let's look at it just like we did with arithmetic sequences. We see that we start with a term, and then we're multiplying that term by some number, and we multiply the next term by that same number, and so on. So really, for a geometric sequence, we multiply each term by a common number to get the next term. So for arithmetic sequences, we were adding the same number to each term to get the next term. Now we're multiplying each number by this, or each term by the same number. So I'll erase this again just like before so we can see. So a sub 1 is still the first term in the sequence. And then r is what we call that common number that we're multiplying by. We call that the common ratio. So for arithmetic sequences, we have the common difference, d for difference. For geometric sequences, we have the common ratio, r for ratio. And the nth term of a geometric sequence is given by a formula. A sub n equals the first term, a sub 1, times r to the n minus 1 power. And again, we're just getting this by looking at our general sequence for it. So let's look at some examples. If a sub 1 equals 3 and r equals 2, then find the nth term of the geometric sequence. I'm plugging into the formula. A sub 1 is 3, r is 2 to the n minus 1 power. I can't simplify that anymore. Despite some of your best attempts on our last unit test, you cannot multiply 3 and 2 together since you're raising 2 to a different power. Do not try. This is not 6 to the n minus 1 power. You are violating every rule of math that has ever been conceived. Please do not. All right. Next question. Given a sequence, find the nth term of the geometric sequence. Well, my first term is 2. And then what am I multiplying by to get the next term? I'm multiplying by negative 5. So r equals negative 5. That means a sub n equals 2 times negative 5 to the n minus 1 power. And again, I cannot simplify this, so do not even try. Leave it this way. Now let's look at graphing this. So we graphed an arithmetic sequence, and we saw that it ended up being a linear function, where the common difference was the slope. Here, if I graph this particular function, and I took the liberty of already coming up with a few values before this, so you wouldn't have to sit here and listen to me try to plug in some numbers here. We get a graph that looks like this. What do you notice about this graph? What kind of a graph is this? It's certainly not linear, it's not quadratic. It is, in fact, exponential. Yes, there was a reason we do this unit after our exponentials unit. So what happens if r is greater than 1? So remember, r is this term, this number that we're raising to a power. It is the base. If r is greater than 1, then we're experiencing exponential growth, just like in this example. If r is a fraction between 0 and 1, we're experiencing decay. And then if r equals 1, then no matter what power I'm raising it to, it's still going to be 1. So that's going to be constant. So we can have growth, decay, or we'll have a constant graph. So this is exponential. Geometric sequences represent exponential functions. Arithmetic sequences represent linear functions. That's an incredibly important distinction, and one that should help you keep track of which is which. Find the 8th term of the geometric sequence. looking at example 2. A1 is 5. I'm multiplying each term by 3 to get the next term, so r equals 3. That means an is 5 times 3 to the n minus 1 power. So the 8th term, a sub 8, is 5 times 3 to the 8 minus 1 power, 5 times 3 to the 7th power, which is 10,935. That's all there is to these kinds of questions. Example 3. Example 3 is another interesting question, and one that takes a bit of time to work out. Find the nth term of the geometric sequence and the 5th term, given that the 3rd term is 63 over 4, and the 6th term is 1,701 over 32. What do we do? How can we go about solving this? Well, we need the nth term, and we need the 5th term, which we'll get after we find the nth term. I know that the 3rd term is going to be the first term times whatever r is to the 3 minus 1 power. So 3 minus 1 we know is the 2nd power. And I'm told that that equals 63 over 4. Similarly, I'm told that the 6th term, that's going to be the first term times r to the 5th power, which equals 1701 over 32. Now, what can I do? How do I solve for anything here? Well, why don't I try first solving for the first term, a sub 1. So from the 3rd term expression that I have, if I solve for a sub 1, I just divided both sides by r squared, and I got a sub 1 equals 63 over 4 times r squared. If I do the same thing here, I get the first term equals 1,701 over 32 times r to the 5th. Now I'm going to set these equal to each other. They both equal the same thing, so I can set these two fractions equal to each other. 63 over 4r squared equals 1701 over 32r to the 5th. I know this looks hideous, but it's just simple algebra. It shouldn't intimidate us. Cross multiply. So 63 times 32 is 2016 r to the 5th. And then 4 times 1,701 is 6,804 times r squared. Divide both sides by r squared. Divide both sides by 2016. I know this is getting messy, I apologize. That's r cubed equals 6804 over 2016. Solve for r. Take the cubed root of both sides. Plug this into a calculator, and you will get r equals 3 over 2 in the end. Yes, all of that work for 3 over 2. If r equals 3 over 2, then the first term is 63. I'm just plugging in to choose one of your formulas. 4 times 3 over 2 squared. Simplify all of that out. You end up with 7. Yes, again, all of that work for something as nice and simple as 7. So now I have the first term, I have r. All right, pause the video if you need any of this other work, but I'm going to erase it so I have some more room to work with. So a1 equals 7. That means the nth term is 7 times 3 over 2 to the n minus 1 power. That was the first thing they wanted me to find. Then they wanted the 5th term. Plug in 5th term, that's 7 times 3 over 2 to the 4th power. 7 times 81 over 16. And you can plug that into a calculator and get an answer, but it'll end up being 567 over 16. And that might simplify, but I don't have a calculator right next to me. So that's all you need to do. Not too bad. In general, those are the kinds of questions we'll ask about geometric sequences, but we can also talk about partial sums of geometric sequences. So again, this is what that expression would look like, the nth partial sum, and there's a formula for this as well. If you'd like the derivation, come and ask me about it. But I'm just going to give you this formula because I'm so generous. The nth partial sum is equal to the first term times 1 minus r to the nth power all over 1 minus r. So all we have to do is use this formula. Example 4, find the partial sum of the first 5 terms of the geometric sequence. That means we want the 5th partial sum. The first term is 1, so a1 equals 1. What is r? What am I multiplying each term by? Multiplying by 0.7. So plug this into your formula. To the nth power, n in this case is 5, all over 1 minus 0.7. And you'll get 2.7731. All right. Find the sum. I really don't understand why this doesn't always come out. So find the sum. We're starting with k equals 1, ending with k equals 5 of 7 times negative 2 over 3 to the kth power. Well, I don't know about you, but I see this expression in here, and I think that looks a whole lot like a geometric sequence. And that means I should be able to just use my geometric sequence partial sum formula. Ending with 5 means I want the 5th partial sum. And why don't you try working the rest of this out on your own? We can talk about this in class. All right? All right. One more thing this section. One more main idea, and that's something called an infinite series. So an expression of this form, where we are adding each term in the sequence, a1 plus a2 plus a3 plus a4 plus, but instead of stopping at an nth term, we are continuing forever. We are adding every single term in this sequence. So those 3 dots mean that we are adding indefinitely. We are not stopping. Well, if we're adding indefinitely, we're adding to infinity. This is what we call an infinite series. And it turns out that the sum of an infinite series can be finite. Let that sink in. The sum of an infinite number of numbers can be a finite number. So that might seem impossible. How can we add an infinite number of numbers but end up at a finite sum? But look at this example. I can keep cutting my one full circle in half. So half, 4th, 8th, 16th, 1 over 32. In this case, this is a geometric sequence. I'm multiplying each term by a common ratio of 1/2. And I can keep cutting that white wedge left in here in half, in half, in half, over and over and over again, an infinite number of times, keep cutting it in half. But no matter how many times I do that, I'm still going to have my same whole. I'm going to have my one full circle. So hopefully that kind of helps you wrap your mind around the idea of adding an infinite number of numbers. I think infinity is really interesting. I can talk a lot about different kinds of infinities. We can talk a lot about sums of infinities. But you'll have to come talk to me on your own about that because we don't have time to delve too much into that in this lesson. So what can we do with infinite geometric series? Well, when we have an infinite geometric series, Kind of like we had up here, just a regular geometric series, except we're not stopping at an nth term. Our sum formula is actually simplified. So we have the sum, s. There's no sub n because we're not stopping. This is the sum of the entire series. And this is the first term over 1 minus r. That's it. Again, this is one of those moments where I think we just need to stop and look and just bask in the simplicity of this formula. I think it's fascinating. Go on ahead, continue making fun of me, but I'm going to keep enjoying it. So, example 6. Find the sum of the infinite geometric series. This series continues forever by these 3 dots here at the end. I use my formula. S equals my first term, a1 equals 2, over 1 minus, I need my r. What am I multiplying each term by? I'm multiplying by 1 over 5. So 2 over 1 minus 1/5 is 4 over 5. If I flip the fraction, I get 10 over 4, which reduces to 5 over 2. So the sum of every single term in this infinite geometric series is 5 over 2. I can't get over how cool that is, that we can use such a simple formula and get an answer like that. So exact and precise. All right, example 7. This is another one of those challenge problems, those fun problems that I love so much. Find the fraction that represents the rational number 2.351, where the 5 and the 1 are repeating. So 5, 1, 5, 1, and so on. How do we get started? I want a fraction. So let's take this a piece at a time. 2.3. 2.3, well, that's equal to 23 over 10, right? 51 thousandths, right? Because the 3 tenths, hundredths, thousandths. So this is 51 over 1,000. And then another 51, that's 10 thousandths, 100 thousandths, so 51 over 100,000. And then the next 51, 100 thousands, millionths, 10 millionths, so 51 over 10 million. And this keeps going. So if I put this together, if I add these fractions, it's 23 over 10 plus 51 over 1,000 plus 51 over 100,000 plus 51 over 10 million plus, and that'll just keep going because the 51 repeats over and over to infinity. So notice here, so ignoring the 23 over 10, everything after that forms its own infinite geometric series. The first term is 51 over 1,000. I'm multiplying each term by 1 over 100 to get to the next term. So that means the sum of that entire infinite geometric series there, by my formula, is my first term over 1 minus r. 51 over 1,000 over 99 over 100. Flip the fractions and multiply. This is 51 over 990. So everything after that 23 over 10 sums to 51 over 990. Thus, 2.351, where the 5 and the 1 are repeating, is 23 over 10 plus 51 over 990. I took this entire thing, and it sums to this nice, simple fraction. That means if I add these two fractions together, 388 over 165. That's my answer. So I can figure out what fraction gives me this number with the repeating decimal. All right, enough of me geeking out over really cool math stuff. Come talk to me about more of this if this interests you. Hopefully some of you have had your interest piqued. Otherwise, rewatch parts of this that confused you, jot down your questions, come ask me before or after class, come to tutoring, and we'll do plenty of practice during class. All right.